Okay, let's continue. Yeah. Okay. So in the last class we were looking at how to form a good voltage reference on chip. The starting point was the observation that if you have a forward bias diode, the voltage across the diode is roughly constant. But the issue was the following: if you change the temperature and measure the same voltage, the diode voltage kind of drops with temperature. This is what we refer to as complementary to absolute temperature, or CTAT. But our goal is to get a voltage reference which is constant with temperature. So the idea was to generate another voltage that is sort of increases with temperature, and then you can scale the two voltages so that their slopes cancel, so that you get a zero slope here. And if I look at the diode voltage, it is essentially Vt ln of, or I will say Kt by Q, natural log of the current by Is. Here the temperature dependence is linear, but due to this Is, the voltage drops with temperature. So if you want to get something that is increasing with temperature, we have to get rid of this. And this you can do it by having another current source, say with a current I1 by N, and call this second voltage VEB2, and you take the difference between the two. And instead of doing this, you can also do the following: you can scale the entire circuit and say that this current is I1 and I have N diodes here. So if this is the case, if the total current is I1 and I have N diodes in parallel, what is the current flowing through single diode here? I1 by N. So that's what happens. And if you now find the voltage between this, if I call it delta VEB, that will be Kt by Q ln of I1 by Is minus Kt by Q into ln of the current flowing through single diode is how much? It is I1 by N by Is. So you simplify it, you get it as Kt by Q natural log of N. So as you see, this fellow is constant. So as you increase temperature, the difference between the diode voltages increases, and this behavior is what we call as PTAT, or proportional to absolute temperature. Now we have two quantities, one that reduces with temperature, another quantity that increases with temperature. So if you can add them with appropriate scaling factors, you can ensure that the slopes cancel and you can get a constant reference. You can. Thanks. So which means all I have to do is this. Let's see if I can make some space. So all I have to do is this: to get my final output, I take the CTAT voltage, which is one diode voltage drop, and add it to the PTAT voltage, which is difference between two diodes, and add it. So the point to always remember is, if I have one single diode, if I have one single diode voltage like this, that is CTAT, that is its voltage drops with temperature. But if I take the difference between two diode voltages, that gives a proportional to absolute temperature here. That is the basic fundamental we will use in all kind of bandgap, all kind of voltage references. So CTAT and PTAT, you add them. So now this is my final output. So if I expand this, I'll have VEB1 plus Kp times, this is VEB1 minus VEB2. So if I simplify this further, I have VEB1 times 1 plus Kp minus Kp times VEB2. So which means to get this output, Vout, I should take VEB1, process it by a gain of 1 plus Kp, VEB2 process with a gain of minus Kp, and this you can simply do it using non-inverting and inverting amplifier stages. I think that's what gave rise to this fellow here. Yeah. So I take VEB1, gave it to non-inverting structure, VEB2 gave it to inverting structure, and get this. So the gain I have here is R2 by R1. Right? So now, of course, here we wanted to have a voltage that is independent of temperature. But what can you say about this gain here? Does it change with temperature or will it not change? It will not change because independently the resistors values can change with temperature. But if you realize both resistors using the same kind of material, both their values will change by the same factor. So the ratio kind of cancels. So this is some thing that we'll commonly use on circuits. Anytime you want some gain to be accurately defined, you try to define it as ratios of two similar quantities, maybe ratios of two resistors, ratios of two capacitors, or it can be ratios of sizes of two MOSFETs, something like this. This ratios will be very tightly controlled on CMOS process. What is not well controlled is the absolute value of resistors. So this gives to the variance. So now if I plug in the circuit, this is what it looks like. But here one issue is the following. Ideally I want the currents in both branches to be equal, but the moment I wire it up like this, on the left side I have I1, right side I have an additional current flowing through R2. So to make the currents equal, a simple fix is to add this current here also. That will keep the currents in both branches equal. But finally the observation was, here I just have to make sure that the diodes are forward biased, and I see that the current is I1 plus this factor. So even if I choose I1 to be 0, the diodes will be forward biased. So the current source is sort of redundant. We can remove it and you get this. So this is the final structure. So let me see if I can, let me copy paste this and see, or let's see. And interesting thing about this circuit is here you have both negative and positive feedback, because you have feedback from the output to both inverting and non-inverting terminal. If you have both positive and negative feedback, what should you ensure? The negative feedback dominates. Particularly at DC, there should be negative feedback around the op-amp, right? Because if there is no DC negative feedback around a high gain op-amp, the bias voltages will not be defined properly. Transistors inside will not be in saturation, and op-amp will no longer behave like an op-amp you want. So here, if you work out, we saw that this is indeed in negative feedback. So this is fine. So let's move on from there. So this is our simple circuit. And the other thing is, it turns out if you calculate this voltage, this comes out to be about 1.12 volt, equal to the bandgap voltage of silicon. Because of this is called as bandgap reference. Okay, so now tell me, I have this structure here. I have to sense two inputs, amplify and give a single-ended output. What kind of circuit you can use here? The 5T OTA you can use. And again, you want to have a very high gain, so you might want to put cascodes or something. So let's say this has a high gain. Now you see that the output you are directly connecting it to resistors. So the small signal gain will be loaded by the resistor branch here. So what can you suggest to do now? We can have a multi-stage structure, we can have a two-stage. So that's what is commonly done. So this is, as of now, the structure I have. Now I have to replace it with a two-stage op-amp. So which means this is no longer my output. Correct? From here I should have a second stage. So what do you think can be used here, PMOS or NMOS for second stage? Which might be better, PMOS or NMOS? Depends, very good point. It depends on what we have here. But there is another consideration. See, let us say I want the final load to be connected to ground. Let us say I have two possibilities, right? Let us say from the op-amp output I can have an NMOS second stage or a PMOS second stage. I want my load to be connected to ground. So which of the two might be easier to use? NMOS. Why? If I were to connect the load here, I will connect to the drain, source or gate of the transistor. Drain. From drain I have to connect it to ground. Which is more easier, you think? For PMOS I can directly connect the load here and get it done, right? Otherwise for NMOS you'll put something to the supply and then you have to put a bypass cap and put the load something, right? So PMOS is slightly more easier, so that's why we use PMOS. I mean, is a consideration, does it make sense? I mean, it's not like you can't use NMOS, but with PMOS it is more easier because you directly connect it to ground and it's done. So I'll do that. So I have the basic thing here. So we'll put the PMOS stage. So the output of, I mean, drain is now your final output. Is that okay? I have the first stage. Second stage is given to the PMOS. The output is tapped from the drain. So now, of course, I should do something to the left side. Ideally, what do you want the currents in these two branches to be? Equal. What is fixing the current in the right side branch? Who's providing current to the right side branch? Huh? PMOS transistor. If I want to have the same current on the left side, what do you suggest we do? Huh? I'll have one more PMOS stage, something like current mirror. Okay, so now earlier when I had only single stage structure, the signs of the op amp was this. Now do you think the signs will change or will it remain the same? Why it will be flipped? Yeah, I mean now we have another inverting stage through the PMOS structure, so which means the signs will be flipped, but otherwise we can work out the same. I'll give it as an exercise. Again, there will be both negative and positive feedback. You work out for which signs the negative feedback dominates. Same thing we did for this structure, but at least intuitively it should make sense. Here the output was fed directly, but here it's sort of getting inverted by the PMOS, so the signs also should flip. So this is one commonly used structure for bandgap reference. And of course now you see that we have a two-stage op amp. So I'm using it in feedback. So what should I do? Should do some kind of compensation. You can do anything, Miller or something, or sometimes you can just put a large cap at one of the nodes and push one of the poles to a very low frequency and compensate. That is up to you. Anything you can do. I will not show compensation. Cool. So now this is a functioning and practically used bandgap reference circuit, but there are some limitations. Huh? Oh yeah, so do you think I should have, yeah, good question. So she's saying that here I had R2, here I conveniently I didn't add it. So is it okay or not okay? Okay, first of all, why was this resistor added? Yeah, remember that when I had the first structure, when I had something like this, the currents in both branches were unequal. So I added the resistor here to make sure the currents in both sides are equal, right? Now in this structure, again my goal is to make sure the same currents are flowing. I have a current source pumping in a constant current. So even if I use R2 or I don't use R2, it's fine. Because now we have a very good current source pumping and making sure the current is constant. But even if we have, it won't make a difference.
Both the N diodes and 1 diode also change. Like the side with N diodes and R1 on the left.
No, it need not be. Why?
That would be negative feedback.
No, that's what. Earlier this is the structure, right? Now what I have done from this feedback connection, I am not feeding the output directly. I am inverting and feeding it. So which means the sign should flip, right? Yeah, I mean, or you work out the loop gain. We did it for this structure, right, in the last class. You repeat it. It's no major thing. Cool. Now, like I told, this is a very commonly used circuit. And what is this output voltage approximately? Let's say 1.12 something. So if this voltage must be 1.12 volt, how much should the supply be at least? Yeah, at least more than 1.12 volt by some minimum overdrive for this. So at least 1.2 or 1.3 or something higher. So this sort of puts restrictions on using this at low voltages. When the supply is 1 volt or so, it's difficult to use the circuit. Secondly, sometimes you don't want the band gap output as your voltage. Let us say you want to get some voltage which is say 0.6 volts or something. Because remember, the whole point of having this reference was I want to have some supply voltage that I want to do using negative feedback. So I am sensing this and comparing with the reference voltage. Right now, if my supply voltage is supposed to be 0.8 volt, I cannot compare my output with 1.12 volt and make decision, right? Because which means now I have to take 1.18, I mean 0.8 and multiply by some factor. Only then I can compare with 1.12. Remember, in all negative feedback, we take some output, we can probably scale it down. Vda times Vout is compared with Vref. So my reference should be smaller than my output, definitely. So which means in this case you can't use this. You should have a smaller reference. So many times we need to generate voltages which are, I will say, fractions of band gap. So that will require us to do some more modifications here. But is the motivation clear why this might not be sufficient for, let us say, feedback loop trying to generate 0.8 volt? Okay. So let's see what we can do to modify this. And before that, let's first write the output voltage here. Okay, erase all this. So let me call this to be EEB1, this to be EEB2. So if I look at my output voltage, so again let me just rewrite the result so that it registers in your mind. Okay, leave it. Okay, if I take one diode voltage VEB1, that is CTAT. Okay, if I take difference between two VEBs, that is a PTAT voltage. And remember, this is essentially Vt times natural log of n. Okay. Now, if I look at my output voltage, it is essentially the drop across R2. Sorry, this is VEB1. Negative feedback will make sure both are at VEB1. Okay. If I look at output now, it is drop across R2 plus VEB1. So this is VEB1. I'll write it this way. Drop across R2, let us say I times R2 plus VEB1. Of course, this is now your CTAT voltage. Now, if this voltage is VEB1, this voltage is VEB2, what can you say about the current? VEB1 minus VEB2 by R1, right? And that's essentially your PTAT, right? So this is VEB1 minus VEB2. This is your PTAT voltage divided by R1 times R2. Same thing, I'm just rewriting so that we can get some idea as to how to get a smaller output voltage. That's all. So CTAT voltage, PTAT voltage. I'm scaling the PTAT voltage by this gain. And as you know, if the gain is realized as ratios of resistor, the gain is accurately well controlled. We are set. Okay, so now my goal is to get an output voltage which is, let us say, a fraction of this output. So let's say I want to get something which is V out by G. So which means here I should have V out by G. First term is divided by G, second term is divided by G. Now tell me, how do I generate this voltage? What is one simple way to get this? Earlier I had R1. Now it seems like R1 should be replaced by G times R1. First term is trivial. So I'll just say this is no longer R1 now. This is now G times R1. This part is CZ. So let me make some space and draw this. So let us say this is G times R. Now the second term is the EB1 by G. Now again, this gain I want it to be well controlled accurately. If that is the case, how do you think we can realize this gain as? I mean, if this gain should be constant, should not change a lot, how do you think we can realize this gain as? Ratios of resistors, because that is something is very well controlled, doesn't change with temperature. So let us say this first term is done. Second term, if I want to do it, I let us say do it as say Rx by Ry. If I do something like this, I am set. Is that okay? Now you can think of it this way. I have a current which is this thing. I have another current which is this quantity, right? So this current is generated because of the current flowing in this resistor. Let us say now I wish to generate a current which is VEB1 by Rx. What can I do here? And if I look at the current flowing through this resistor, I get the first term, correct? Now I want to get a current which is VEB1 by Rx. Look at the circuit here. What can I change here so that I can get a current that is equal to VEB1 by Rx? Yeah, I have VEB1. I want to get VEB1 by Rx. What do you need to do? I just put a resistor with a value Rx there. So if I do that, so now I'll call this the PTAT current. Of course, it is not very correct to call, but I'll call it IPTAT. I'll call it ICTAT. This is kind of assuming resistors are not varying with temperature, because if the resistors vary with temperature, this current will not be having the PTAT behavior. Okay, this voltage is PTAT, but this voltage by current need not be a PTAT quantity. I'm just assuming the resistor is constant for now. So now I have the PTAT current flowing on the left side branch. I have the CTAT current flowing in the right side branch, or I mean the left, okay, yeah, these two branches. Now seems like to get my scaled output, I should pass this current through a resistor R2 and pass this current through another resistor Ry and add the two voltages. Now in a circuit in circuits, do you think adding voltages are easy or current is easy? Voltage or current? Huh? Why not voltage? How do you add currents? Yeah, just join two wires. KCL will ensure that the current is summed up. So this is the most simplest thing to do. So can you suggest something that we can do here so that this can be thought of as adding currents? If I choose Ry to be equal to R2, so let me write it this way. So if as of now the situation is this, it is IPTA times R2, ICTA times Ry. Now the situation seems like I need to add two voltages. If I have to reduce it to an easier operation, you choose Ry to be equal to R2, then it essentially becomes sum of the currents. Make sense? So all I have to do is sum up these two currents, make it flow through a resistor R2, and I tap the voltage from R2 and I'm set. I have PTAT, I have CTAT current. So where is it getting summed up here? Yeah, in the okay, in this branch. Yeah, what is happening to this display? Okay. Okay. Essentially, this is this PTAT current plus CTAT current. So let me take it to next page to. Yeah. So the current flowing through R2 is the sum. So where should I take my output right now? what should I call as my output now? Is this voltage my Vout or something else? Drop across R2 is my Vout. Okay, so this is no longer my output. Okay, so drop across R2 is my output. So now let us say, but I mean, taking a differential output is not, in the sense, a reference, I want a single-ended reference. So let us say I don't want to define this as my output, I want to get a single-ended output. So I have a current here, that is the required quantity. All I need to do is pass it through a resistor and take it with, voltage across it. So can you suggest some modification I can do so that I can take the output as a single-ended quantity? Huh? You can use op amp. Why do you want to? Okay, to take the difference between the two. I mean, you can do all that, but let's look at really simple things. Right? There's nothing wrong in it. See, as of now, the issue is the voltage is obtained like this, correct? If I want my output to be single-ended, what can you say about the resistor R2? What can you say about one end of the resistor R2? It should be grounded. Here I can't go and ground it, right? But I have the required current. If I pass this current through a grounded resistor R2, I get the voltage. I have the current. What can I do? I can mirror it to another branch and get this done. That's all we do. So which means I have to take an identical PMOS transistor, I pass it through R2, and this is my view. So which means now, do I need to have this R2 here? It is not necessary. Is that clear? R2 is no longer needed here. Oops. This R2. This resistor is no longer needed in the circuit. Okay. Because all I want to get is a PTAT current, CTAT current. So this is VEB1. So VEB1 by Rx gives the CTAT current. Similarly, difference between the VEBs by GR1 gives the PTAT current. That is nicely getting summed up here. That I am nicely mirroring it and passing it through R. So this way I can get Vout. Here Vout will be VEB1 by some G plus delta VEB times Kp by G. Or if you are to write it clearly, let's write it completely. I copy paste this expression. This is R2 and G is essentially I just rewritten the same thing. That's it. Okay, but before we conclude that this circuit will work, again look at the circuit. Tell me if there is some missing point here. Huh? Exactly, the currents in these two branches, they are no longer equal. Correct? Because remember, I want to have the same currents flowing through the two diodes. As of now, the current flowing through the right side diode is IPTAT. What can you say about the current flowing through the left side diode now? Yeah, it is the sum of the PTAT and CTAT currents. So which means now this as such cannot be used. So what modification I can do so that I have only the PTAT current flowing here? If I put another resistor Rx here on the left side to ground, so let me see, this is VEB1. I have another resistor Rx. So this additional resistor will bleed out the CTAT current here. So which means I get the PTAT current. So this variant is often referred to as fractional bandgap for obvious reasons, because this can generate fractions of bandgap voltage, and it's very suitable when your supply is very low, say 1 volt or so. And I mean, now this gives a very nice control, because now I have the current. So by changing the resistor value, I can get different voltages, right? So now I can basically mirror this current, pass to another resistor, let us say R3. This will be a different reference voltage. All I have to make sure is the gains don't change with temperature, which means all resistors must be realized using the same kind of material or same kind of resistor, that's all. And I made sure they are matched, then I am set. Okay. Cool. Any questions still now?
The reference voltage it generates, it feeds it back to itself.
Oh, this we'll see. I mean, as of now, we have generated the reference. How this is going to be used to get a supply, that we'll see. This will not be fed back to this itself. It will be a different system. Awesome.